Moving coil galvanometer. Moving coil galvanometer. So we can define moving coil galvanometer. It is an instrument. It is an instrument used for detection. It is an instrument used for detection and measurement of small electric currents. It is an instrument used for detection and measurement of small electric currents. We can write down the principle of moving coil galvanometer. It is based on that principle that when a current carrying coil is placed in a magnetic field, it experiences a torque due to which the coil rotates. When a current carrying coil is placed in a magnetic field, it experiences a torque. Now we can describe the working of a moving coil galvanometer. We can describe working of a moving coil galvanometer. This is a cylindrical magnetic north pole or horseshoe magnet, or magnetic north pole of horseshoe magnet, and a rectangular coil PQRS prime will be suspended by a suspension wire which is made of phosphor bronze. This is an insulated copper wire which is wound in the shape of a rectangle around a cylindrical core of soft iron. This is a rectangular coil. So here an insulated copper wire is wound in a shape of rectangle, and the lower end of this copper wire is connected to a spring or lower suspension wire. The lower end of this rectangular coil PQRS prime is attached to a spring or lower suspension wire, and this is the cylindrical core core L, which is made of soft iron. So we have the cylindrical magnetic north pole, which produces a strong magnetic field. This is the cylindrical north pole, and a rectangular coil PQRS prime is suspended in the magnetic field, in the radial magnetic field produced by this cylindrical north pole and south pole. And we have to consider another cylindrical south pole or south pole of horseshoe magnet. And the rectangular coil PQRS prime is suspended by this suspension wire which is made of phosphor bronze, and a concave mirror M. A concave mirror M is attached to this suspension wire or this phosphor bronze strip. This is the suspension wire or phosphor bronze strip. Suspension wire, or it is also known as phosphor bronze strip, because this suspension wire is made of phosphor bronze. In this case, a current I is sent through this rectangular coil PQRS prime. Current flows upwards through the arm RS prime, and current I flows downwards through the arm PQ. In this way, the electric current I will flow through this rectangular coil PQRS prime placed in a radial magnetic field between two cylindrical north pole and south pole. B is the magnetic field induction which acts towards the center of the spherical region enclosed by this cylindrical north pole and south pole, and the coil PQRS prime is placed at the center of this cylindrical region between this north pole and south pole. Here the magnetic field induction B acts away from north pole towards south pole, and this magnetic field B is acting towards the center of this rectangular coil PQRS prime. Let PQRS prime be a rectangular coil. PQRS prime be a rectangular coil which is made of insulated copper wire. Let PQRS prime be a rectangular coil having let PQRS prime be the rectangular coil having n number of turns of insulated copper wire carrying an electric current I. Carrying an electric current I which is suspended. That means the rectangular coil PQRS prime is suspended in a radial magnetic field. Of magnetic field induction vector B. Produced by the two strong cylindrical magnetic north pole and south pole. The rectangular coil PQRS prime is suspended in a radial magnetic field of field induction vector B produced by the two cylindrical magnetic north pole and south pole. Therefore, the torque experienced by the rectangular coil of area of cross section A in this radial magnetic field of field induction vector B is given by tau equal nia B sin alpha. Nia B sin alpha, where capital N is the number of turns, I is the electric current, A is the area of cross section of the rectangular coil PQRS prime, and B is the magnetic field induction of the radial magnetic field produced by the cylindrical north pole and south pole. As the magnetic field is radial, the angle which the area of cross section vector A makes with the direction of magnetic field B is alpha equal 90 degree. Therefore, vector A is perpendicular to vector B. This is the rectangular coil which is suspended by a suspension wire. PQRS prime be the rectangular coil. PQRS prime be the rectangular coil which is suspended in vertical plane and magnetic field induction vector B acts towards right. Area vector A is perpendicular to the plane of the coil. Vector A is the area vector of the cross section of the coil. In this case, angle subtended by vector A with vector B is alpha, which is equal to 90 degree. Therefore, torque tau will be equal to nia B sin 90 degree. Therefore, tau is equal to nia B, which is equation 2. Tau equal nia B, which is equation 2. Due to this torque, the coil PQRS prime rotates about its own axis, that is about the phosphor bronze strip. So in the diagram, this is what the direction of rotation of the coil. As a result, this torque rotates the coil about its own axis. As a result, phosphor bronze strip gets twisted. And a restoring torque comes into play. In the phosphor bronze strip. It should be strip only, strip which would try to rotate the coil back to the original position, restore the coil back to the original position. Vector B acts horizontally towards right, and the coil is suspended in a vertical plane. Area vector A makes an angle alpha equal 90 degree with the magnetic field induction. This is the suspension wire, or what phosphor bronze strip, using by which the coil is suspended in a radial magnetic field. And in this position, a torque tau will be which is equal to nia b will act, and due to this torque, under the action of this torque, the rectangular coil will rotate anti-clockwise with respect to the upper end of the coil, and restoring torque tau r will be acting vertically downwards, and deflecting torque tau will act vertically upwards, but restoring torque will act vertically downwards. And this restoring torque would try to restore the coil back to its original position. Hence the restoring acting in the phosphor bronze strip. Restoring torque acting in the phosphor bronze strip is given by tau r proportional theta. Therefore, tau r equal k theta. That is equation 2, where k equal tau r divided by theta. K equal tau r divided by theta, which is the restoring torque per unit angle of twist. Where k is the restoring torque per unit angle of twist of the phosphor bronze strip. Therefore, k equal tau r by theta. That means restoring torque divided by angle of twist, which is the restoring torque per unit angle of twist of the phosphor bronze strip. Tau r equal k theta, where theta is the angle of twist. Produced in the phosphor bronze tube, using by which the rectangular coil PQRS prime is suspended in radial magnetic field. Theta is the angle of twist produced in the copper phosphor bronze tube, which is measured by the angle of deflection of a ray of light incident on the concave mirror attached to the suspension strip. Now we can consider a diagram of a moving coil galvanometer. In the diagram, this is a concave mirror which is attached to the suspension wire, or which is made of phosphor bronze strip. In the diagram, from a lamp or from a source of light, from this lamp or source of light, a ray will be generated, and this ray will be incident on this concave mirror attached to the suspension wire, and after reflection it will follow the laws of reflection, and after reflection, reflected ray will be traveling towards translucent scale, and it will strike this scale at the flying spot, and this is the refracted ray refracted from the concave mirror attached to the suspension wire. And the angle of twist is theta. Theta is the angle of twist which is measured in translucent scale. In this case, reflected ray will be traveling towards the translucent scale. When the coil, now we can write that this is the coil in the diagram, and the coil rotates anti-clockwise with respect to the upper end of the coil under the action of the torque tau, which acts along the suspension wire vertically upwards, and the restoring torque tau r will act vertically downwards. When the coil comes to rest, that is when it attains equilibrium, comma, the restoring torque under bracket tau r will balance. The restoring torque tau r will balance the deflecting torque tau. Due to deflecting torque, the coil will rotate anti-clockwise, and due to restoring torque, the coil will rotate clockwise. So in this equilibrium condition, when the coil does not rotate, in that case, in this equilibrium position of the coil, deflecting torque will be equal to restoring torque. Deflecting torque will be equal to restoring torque, or tau equal tau r, or nia b, equal k theta, because restoring torque acting on the coil will be equal to k theta, where now the deflecting torque will be acting vertically upwards along the suspension wire, and due to this deflecting torque, the coil will be deflected and it will rotate anti-clockwise. And now restoring torque tau r will act vertically downwards along the same suspension wire, and this is the coil, and which is wound over the cylindrical core made of soft iron. In the diagram, magnetic field vector B acts horizontally towards right, and this current carrying rectangular coil will rotate anti-clockwise with respect to the upper end under the action of deflecting torque, and as the property of elasticity, restoring torque tau r will act along the same straight line, and at this equilibrium tau equal tau r. At this equilibrium condition, tau equal tau r, or I equal k divided by NBA into theta. I will be equal k divided by NBA into theta. Therefore, I equal g theta, where g is equal to k divided by NBA. Finally we get I equal g dot theta, which is the current flowing through the moving coil galvanometer, the coil of the moving coil galvanometer. I is equal g dot theta, which is the current flowing through the coil of the moving coil galvanometer. Therefore, I will be proportional to theta, because the galvanometer constant G, which is equal to K divided by NBA, will be constant. Hence the current flowing through the moving coil galvanometer, will be directly proportional to the angle of twist. The current flowing through the coil of a moving coil galvanometer is directly proportional to the angle of deflection produced in the suspension wire, that is produced in the phosphor bronze strip. Under bracket suspension wire.